Have you ever clicked buy now on a website and just completely zoned out for that split second before the payment successful screen pops up?
Oh, absolutely.
Right. You get the little spinning wheel, maybe a green check mark appears, and boom, your new shoes or your, monthly coffee subscription is on its way.
Yeah, you don't even think about it.
Exactly. But have you ever actually stopped to wonder what happens in that one tiny invisible second? Today, we are taking a deep dive into the invisible, really high-stakes infrastructure of the internet.
It is a wild world back there.
It really is. And we have a fascinating stack of sources today. It's essentially a highly technical developer playbook from a company called Integrate Payments.
Mm-hmm.
We're looking at their internal documentation for tools with names like QuickClick, Direct Post, the Query API, and the three-step Redirect API.
Which sound intimidating, but they're incredibly clever.
Right. And our mission for this deep dive is to decode all this heavy developer documentation. We want to reveal the really clever tricks used to move your money safely while constantly outsmarting fraudsters.
And that single second of processing you mentioned earlier,
Yeah.
it's genuinely a marvel of modern engineering.
Yeah.
To really appreciate what these developer documents are outlining, we sort of have to look at the historical context.
Okay.
Because in the early days of the internet, handling credit cards was essentially a wild west of liability. I mean, merchants were literally storing credit card numbers in plain text on highly insecure local servers.
Oh, man. Just plain text.
Plain text. It was a hacker's absolute paradise.
Wow.
But today, as we can see in these sources, the process is this highly orchestrated, almost paranoid dance of cryptography, tokenization, and data routing.
Paranoia is probably a good thing when it comes to my bank account.
Definitely. Every single step outlined in this playbook is designed with the baseline assumption that an attacker is actively trying to intercept the data right now.
And the sources break down several different ways a business can accept money. It ranges from super simple setups for like a local bakery all the way to incredibly complex integrations for massive enterprise corporations. Okay, let's unpack this. Let's start with the absolute simplest option they offer, which they call QuickClick.
Yeah, quick.
The documentation describes this as basically the easiest way for a merchant to start taking money. They use these really simple HTML buttons that a business owner can drop right onto their existing website.
Just copy and paste.
Exactly. The playbook mentions three main types, which are a shopping cart button, a fixed price button, and a donation or payment button.
But the hidden complexity inside those seemingly basic buttons is what really stands out here. Because for a small business owner, it feels like they're just copying a tiny snippet of code.
Right, it looks like nothing.
But that HTML code actually contains highly customizable variables. The system handles all the pricing rules automatically without the merchant ever needing to hire a software engineer.
I actually found the customizability detailed in the docs really surprising. Like, developers can add drop-down menus right next to the button. So if you are buying a t-shirt, the underlying code uses a variable to let you pick small, medium, or large, and it actually adjusts the inventory accordingly.
Yep, all from the button.
They can even add text entry fields for things like custom monograms. And my absolute favorite part was the logic behind shipping thresholds.
Oh, the shipping rules are brilliant.
Right. A developer can code a rule straight into the button that says, hey, if the domestic cart hits exactly $100, automatically drop the shipping cost to 0. It just all happens seamlessly in the background.
The challenge with that background magic, though, is the inherent vulnerability of the web itself.
Because it's public.
Exactly. Because this quick click button is just standard HTML sitting on a public-facing website.
Yeah.
It's entirely exposed. A malicious user with even a fundamental understanding of how web browsers work could just right-click your web page, hit Inspect Element, and physically alter the HTML code right there on their screen.
That sounds dangerous.
It is. If you are selling a high-end camera for $500, they could manually change the item price variable in their browser to $1 and just click buy.
Which means the merchant would suddenly be shipping out a $500 camera for $1.
Right.
Which would completely ruin their margins, probably put them out of business.
That is precisely why the documentation stresses a security measure called key verification and hashing.
Hashing.
Yeah. Hashing is a one-way cryptographic process. When the merchant originally creates that HTML button in their account, the payment system generates a complex, invisible verification hash based on the true price, the item ID, the shipping cost, all the vital details combined.
Okay, so it locks it in.
Think of that hash as a digital, unbreakable wax seal on a letter.
Oh, I like that.
If a fraudster alters the price on their screen to $1, The data they submit no longer matches the unique geometry of that original wax seal.
So the system knows it was tampered with.
Exactly. The payment gateway instantly recognizes the tampering, rejects the transaction entirely, and locks the code down.
Reading through the developer notes, I also caught a really fun, slightly annoying technical quirk about how these buttons interact with the real world.
The Safari issue.
Yes, the documentation specifically warns developers that QuickClick does not support iframes.
Right.
And an iframe is basically just a window on your web page that shows another web page inside it. It turns out this is blocked because Safari, Apple's web browser, has documented features and bugs that aggressively block third-party cookies to protect user privacy.
It's a huge headache for developers.
Yeah, so if a developer tries to run this quick-click checkout inside an iframe on Safari, the browser's privacy shields interpret it as tracking, and the entire checkout process just shatters. It completely breaks.
It is a perfect reminder that financial technology does not exist in a vacuum. I would actually ask you, the listener, to think about how many times you have interacted with a simple buy now or donate button on a local charity's website.
You just click it and assume it works?
Exactly. You are likely completely unaware of the complex cryptographic wax seal protecting that transaction, or the massive privacy wars happening between web browsers in the background just to ensure your session data isn't blocked.
QuickClick clearly works beautifully if you're a local shop just trying to sell a few items. But the moment you become a larger retailer, relying on a simple HTML button isn't really going to cut it anymore.
No, you need more control.
You need the checkout experience to be entirely custom to your brand, which means we have to transition to the next tool in the playbook, which is the Direct Post API.
This is where things get serious.
And just to clarify for everyone, an API, or application programming interface, is essentially a digital waiter. It takes a request from one software system, carries it to another system, and brings the response back.
What's fascinating here is how Direct Post fundamentally shifts the immense burden of data security.
Yeah.
Well, when a business builds a custom checkout experience, their own computer servers are suddenly interacting with raw, unencrypted credit card data. And the documentation makes it very clear that Visa and MasterCard have instituted incredibly strict payment card industry, or PCI, data security standards.
Right, PCI compliance. We hear about that all the time.
We have all seen the headlines over the last decade about massive retail chains getting hacked and millions of credit card numbers leaking. If a merchant server is breached and card data is stolen, they face business-ending fines and liability.
Which is terrifying for a business owner. But the developer docs introduce a specific solution for this called the Customer Vault.
Yes, the Customer Vault. It functions like a highly fortified digital safe located completely off-site. Instead of the merchant storing your credit card number in their local, potentially vulnerable database, their API sends your data through an SSL connection.
Secure sockets layer.
Exactly. You can picture SSL as a heavily armored, encrypted tunnel on the internet. That tunnel leads directly to the payment gateway's Level 1 PCI-certified data facility.
So the data leaves the merchant's hands immediately.
Right. The facility locks the actual card data away and hands the merchant back a safe token.
Yeah.
And this token is just a meaningless random string of alphanumeric characters.
Just gibberish.
Pure gibberish. From that point forward, if the merchant wants to charge you again for a future purchase, they just send the token down the API tunnel. The actual 16-digit credit card number never lives on the merchant's local servers at all.
It's essentially like going to a fancy restaurant and handing the attendant your coat. They give you a small numbered ticket in return.
Yeah, that's a great way to look at it.
If a pickpocket steals that little cardboard ticket out of your pocket later that night, they can't wear it to stay warm. The ticket is useless to anyone except the specific coat check it belongs to.
Exactly.
But Direct Post isn't just about consumer shopping carts. The sources spend a lot of time detailing something called Level 3 processing.
Level 3 processing is a completely different beast. It is crucial for B2B business to business or government purchasing.
Because they need more details.
Much more. When a federal agency or a massive corporation buys something, they don't just want a credit card statement with a vague line item that says, office supplies, $5,000. Their internal auditors require intense, granular data tracking to prevent embezzlement and manage complex departmental budgets.
Granular almost feels like an understatement when you look at the actual code requirements here. The API demands highly specific variables for these transactions to even be approved.
It's a lot of data.
We are talking about data fields like summary commodity code, which is a standardized international description of the overall goods being supplied. It asks for the tax amount, the ultra-taxed, and even a duty amount if the goods are crossing international borders.
The sheer volume of bureaucratic paperwork happening in milliseconds behind the scenes is staggering.
It really is.
And developers have to build robust systems to pass all of this exact data flawlessly every single time. Which raises an important question. How does a software engineer actually test a system that complex without accidentally spending thousands of real dollars?
Or triggering real government audits every time they run a diagnostic script.
Exactly.
I was reading through the sandbox documentation and actually laughed out loud when I saw how they test this. The playbook gives developers literal cheat codes for financial software.
They do.
There is a specific demo key provided, which is 3785894. If a developer wants to test a successful purchase, they don't use their own personal credit card. They are told to pass a fake Visa card. It's literally just a string of fours ending in 1111, along with a generic expiration date of 1025.
But testing a successful purchase is really only half the battle. A truly robust system needs to know how to handle catastrophic failures and user errors gracefully.
And the documentation covers that brilliantly, too. If the developer wants to trigger an intentional decline error to ensure their website correctly pops up a red warning message for the user, they simply program the test script to pass a purchase amount of less than $1.
Just like that.
Yeah. The system automatically reads any sub-dollar amount as a hard decline. And if they want to simulate what happens when a user types in the correct security code, they pass 999 as the CVV. Passing 77777 simulates a verified ZIP code match. It lets them stress test every possible failure point in a completely contained environment.
It allows them to break things on purpose without touching real banking networks. But even with the Direct Post API and the Customer Vault handling tokenization, there remains a slight architectural vulnerability.
Right.
In a standard Direct Post setup, the customer's raw credit card data still briefly touches the merchant server for a microsecond before it is shuttled through that armored SSL tunnel to the vault.
Just for a split second.
But even that tiny fraction of contact requires the merchant to maintain a significant, expensive level of PCI compliance.
Here's where it gets really interesting. The developers at Integrate Payments engineered a magic trick to bypass this problem entirely. It is called the three-step redirect API.
It is brilliant.
The fundamental problem they are solving is this. How do you keep the user seamlessly on your custom-branded website, but mathematically guarantee that your server never, ever touches their credit card data, not even for a millisecond?
It is an incredibly elegant piece of software architecture. We can break down the 3 steps to see how it completely isolates the merchant from liability.
Let's do it.
Step 1 begins the moment the customer clicks checkout. Behind the scenes, the merchant server secretly pings the payment gateway and says, "Hey, I have a customer about to buy a shirt for $20, and provides a redirect URL. The gateway registers this pending transaction and hands back a special, unique form URL.
Step 2 is where the actual sleight of hand occurs.
Exactly.
The merchant generates a payment form on the screen for the customer, but the destination of that HTML form is secretly set to the special form URL the gateway just provided.
So when the customer types in their credit card number and hits submit,
The data does not go to the merchant server. It shoots directly from the customer's web browser straight to the highly secure payment gateway. It completely bypasses the merchant's infrastructure.
the gateway grabs the sensitive data, safely stores it, generates a secure token aid, and then transparently redirects the customer's browser back to the merchant's website using that redirect URL from step 1.
The speed of this redirection is so fast the customer simply perceives a brief loading animation.
Yes. And finally, we reach step 3. The customer lands back on the merchant's confirmation page. The merchant server detects the returning customer who brings that safe token aid back with them in the background.
And then,
The merchant server takes that harmless token, pairs it with their own secret API key, and sends one final ping to the gateway to officially finalize the charge.
if I had to use a real-world analogy to map this out, imagine you are in an electronics store buying a massive television. Instead of handing your physical credit card to the store cashier, where a skimmer might be installed or someone might memorize the numbers, the cashier hands you a heavy, locked steel box with a tiny slot in the top.
Okay.
You slide your card into the slot. Suddenly, an armed guard from a secure bank vault walks into the store, takes the locked box directly to the bank, processes the payment, and returns to hand the cashier a simple receipt that just says paid. The local store manager never even saw the plastic of your card, let alone the numbers.
That physical proxy is exactly what is happening digitally with a three-step redirect. It virtually eliminates the merchant's PCI compliance headache because their digital environment is completely insulated from the toxic asset of raw credit card data.
It's ingenious.
It is. But as the playbook goes on to show, technology and consumer behavior refuse to sit still. Just as merchants adapted to these complex redirect APIs, consumers decided they didn't want to manually type their card numbers into web forms anymore at all.
That brings us into the era of modern digital wallets.
Yes.
The documentation dedicates a significant section to the integration of Apple Pay and Google Pay. Unsurprisingly, the rules governing these tech giants are incredibly strict.
Very strict. When a customer uses a digital wallet, the data payload the merchant receives, what the API documentation specifically refers to as Apple Pay payment data or Google Pay payment data, is a heavily encrypted blob of information.
So they can't even read it.
Not at all. The merchant cannot read it or alter it. They are simply a courier passing it straight to the gateway.
The developer docs highlight a fascinating conflict resolution rule about this encrypted blob. Let's say a customer is checking out on a boutique's website. They manually typed out their shipping address and ZIP code on the site's form, but then they hit the Google Pay button to finalize the payment.
Happens all the time.
If there's a mismatch between the ZIP code the merchant's website collected and the ZIP code embedded inside the encrypted Google Pay token, the gateway is programmed to always prefer the Google Pay token.
It overrides the typed input.
Exactly. The system assumes that the data in the customer's digital wallet is the ultimate source of truth, because that is the data the customer explicitly authenticated with their biometric Face ID or fingerprint.
If we connect this to the bigger picture, it's all about trusting the most cryptographically secure point of interaction. And this principle leads us directly into what might be the most complex area of modern payments covered in the sources: stored credentials.
The recurring payments.
Right. The industry relies heavily on two specific acronyms here: CIT and MIT.
Let's break those down. CIT stands for Customer-Initiated Transactions, and MIT stands for Merchant-Initiated Transactions.
Simple enough.
Right. When you are sitting at your computer, actively clicking a checkout button and authenticating a purchase, that is a CIT. You, the customer, are initiating it in real time. But when your Netflix subscription automatically charges you on the 15th of the month while you are sound asleep, that is an MIT. The merchant is initiating it based on a previous agreement.
And the credit card brands, Visa, MasterCard, Discover, they care deeply about this distinction. They demand to know exactly who is pulling the trigger on every single charge to prevent unauthorized billing.
Makes sense.
If a customer signs up for a recurring subscription, the documentation dictates a rigid sequence. The very first charge must be explicitly flagged as a customer-initiated transaction, or CIT. This is the moment you are storing the credential.
The gateway generates a unique initial transaction ID for that very first charge. You can think of it like a digital permission slip that the customer signs.
Once that permission slip is generated, every single charge after that month 2, month 3, month 4 must be flagged as a merchant-initiated transaction, or MIT.
Got it.
And, crucially, the merchant software must attach that original initial transaction ID to every single subsequent MIT request. It creates an unbroken digital paper trail. The merchant is essentially waiving that original permission slip at Visa every month, proving that the sleeping customer explicitly agreed to this recurring charge months ago.
There is a surprisingly strict rule buried in the text about these permission slips that immediately made me think of a shared human annoyance.
Oh.
We all know the mild panic of having a credit card expire or losing it and getting a new one in the mail.
The worst.
You suddenly realize you have to log into 15 different streaming services and utility companies to update your payment info. According to the API docs, if you have been paying for a subscription with a Visa card for a year, the merchant has your Visa initial transaction ID on file.
Right.
But if you decide to swap it out and put a new MasterCard on file instead, the merchant absolutely cannot just reuse the old transaction ID for the new card.
And the underlying architecture explains why. The major card brands track these card-on-file agreements separately on their own proprietary, heavily guarded networks. An initial transaction ID generated for a Visa is entirely meaningless to MasterCard's network. It is basically speaking a completely different language.
So the merchant software has to force the system to run a brand new customer-initiated transaction for the MasterCard to generate a fresh, network-specific ID.
Yes.
The documentation actually includes a stern warning to developers. If you get lazy with your code and try to reuse the old Visa ID on a new MasterCard, it will lead to settlement failures or downgrades.
Which is bad news.
Very bad. That translates to the merchant getting hit with punishingly high processing fees or having the transactions flat out rejected.
Managing this massive web of rules, the tokens, the CITs, the MITs, the mismatched ZIP codes, it generates an absolute ocean of data. Which brings us to the final piece of the puzzle in these sources. How do businesses actually keep track of it all without drowning in spreadsheets?
So what does this all mean for the poor accounting department trying to balance the books at the end of the month?
They need help.
Enter the Query API. This entire section of the playbook is dedicated strictly to data retrieval.
When a business processes tens of thousands of transactions a day, having an accountant log into a web dashboard to manually click around and download CSV files is just impossible. The Query API allows a merchant's custom accounting software to automatically talk to the payment gateway and pull detailed reports in an XML format.
And XML is essentially a universal text language that different computer systems use to structure data, allowing them to talk to each other without needing a human to translate.
Exactly.
The filters they can use to pull this XML data are incredibly specific. A developer can tell the API to only return data where the transaction type is CC for credit card or C for check. They can filter by action type, asking the database to only show sales, or specifically isolate refunds and voids to audit return rates.
It gives the merchant the power to fully automate their reconciliation process. At 2 in the morning, their local servers can quietly ask the gateway, "Send me every settled credit card transaction from yesterday," and the internal ledgers are perfectly updated before the accounting team even wakes up.
The Query API isn't just for basic end-of-day accounting, though. Looking at the parameters you can search for, there are some wildly specific tracking capabilities.
The granularity is amazing.
For example, if a merchant is accepting ACH payments, which stands for Automated Clearinghouse, basically the digital version of writing a paper check, they can literally query the API database by a customer's driver's license number or their driver's license date.
That is incredibly specific.
It is. The system uses this specific data to ping national bad check writer databases in real time to catch serial fraudsters who hop from state to state.
The level of tracking provides absolute, total visibility into the life cycle of a payment.
It gets even more granular than a driver's license. You can query the database by a variable called mobile device nickname.
Oh, wow.
Yeah. Let's say a plumbing company has 20 different repair vans out in the field, and each plumber is using a mobile card swiper attached to their phone. The accountant can pull a report specifically for transactions processed by a device named Jim's iPhone.
That's wild.
They can track every single credit card swipe down to the exact piece of physical hardware sitting in a specific employee's hand on the other side of the city.
It really brings us full circle on just how much infrastructure is built around the simple act of moving money from point A to point B.
It does. To summarize this deep dive, we started with what looks like a simple quick-click HTML button on a web page. But beneath the surface of that button is a sprawling labyrinth of security.
Endless security.
We have cryptographic verification hashes acting like wax seals to stop price tampering. We have customer vaults and armored SSL tunnels trading sensitive credit card numbers for meaningless tokens to satisfy massive PCI compliance liabilities.
And the redirect tricks.
Right. We explored the three-step redirect API acting like a digital armored guard to keep merchant servers perfectly insulated. We unpack the unbending rules for encrypted Apple Pay blobs and the digital permission slips required for recurring MIT subscriptions.
And finally, the Query API.
And finally, an all-seeing Query API to keep the paper trail organized down to the specific smartphone used to swipe a card. All of that invisible automation, tokenization, and redirection happens in the roughly 2 seconds it takes you to check out. The digital world is far more physical and far more structured behind the curtain than it ever appears on our screens.
It is an architectural triumph of modern commerce.
Mm-hmm.
And I'll leave you with a final thought to mull over.
Okay.
The next time you are checking out on your favorite website and you casually click that little checkbox that says "Save this card for later," consider who actually holds your data. Because as we have learned today, you aren't really giving your card to your favorite online store.
You're giving it to the vault.
Exactly. You are authorizing a deeply complex ecosystem of external vaults, cryptographic tokens, and gateway middlemen to speak on your behalf. This raises an important question. What else in our daily digital lives is built entirely on this kind of invisible, proxy-based trust?
That is a brilliant note to end on. A huge thank you to you, our listener, for taking this deep dive with us today. We will catch you next time as we continue to explore the hidden layers of the world around us.